Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Tencent AI RFew, Guided Self-Evolution for Language Models via Challenger-Solver Self-Play. This work starts from the long-standing goal of building AI systems that can improve themselves without relying on massive human-labeled datasets. In principle, self-play should let models generate their own training data and feedback. But in language tasks, existing self-evolving systems tend to plateau quickly or even get worse over time. The authors identify several core failure modes: concept drift, where the model's notion of the task slowly shifts; diversity collapse, where generated data becomes repetitive and low entropy; and misevolution, where the model reinforces its own biases instead of correcting them. The central challenge is to design a self-evolution process that remains stable and controllable, while still using very little human supervision. To address these issues, the paper introduces RFew, a guided self-evolving framework for large language models. RFew is built around a challenger-solver self-play setup. Instead of letting the model drift freely, it injects lightweight human oversight, using a few human-labeled examples as in-context anchors. The challenger uses these examples to generate synthetic questions, while the solver is trained on a mixture of human and synthetic data. Crucially, the solver's training follows an online curriculum that prioritizes tasks at the right difficulty level, helping the model progress steadily without collapsing or drifting. In RFew, the challenger and solver co-evolve. At each iteration, the challenger is tasked with generating new questions that are neither trivial nor impossible, but instead lie near the current boundary of the solver's abilities. To avoid drifting away from the true task, the challenger is grounded using a small batch of human-labeled examples provided in context. The solver then attempts to answer both these human questions and the challenger's synthetic questions. An online curriculum mechanism evaluates the difficulty of each example and selects those that are appropriately challenging for the solver at that stage of training. This loop repeats, gradually pushing the solver to handle more complex reasoning tasks. A key design choice in RFew is how it uses human data. Instead of large-scale supervised training, the framework relies on a very small fraction of human-labeled examples. These examples serve two roles. First, they are fed to the challenger as in-context demonstrations, anchoring its question generation to realistic distributions and preventing drift. Second, they are mixed with synthetic questions in the solver's training batches, ensuring that the solver remains calibrated to genuine human-authored tasks. The authors show that using only 1 to 5% of the human data used by some prior systems is enough to guide self-evolution effectively. When human data is sampled to match specific domains, it can further boost performance in those categories. The authors compare RFew to several self-evolving baselines, including R0, Absolute Zero, and Spice. R0 is a prior self-play method that tends to plateau early and can become unstable over time. In contrast, RFew maintains improvement for longer and reaches higher final accuracy on both math and general reasoning benchmarks. The results show that RFew consistently outperforms these baselines, while also exhibiting smoother and more stable training curves. This suggests that the combination of grounded question generation and curriculum-based training effectively mitigates the instability seen in earlier self-evolution approaches. Using Qwen 3.8b base as the solver model, RFew delivers strong quantitative gains. On math benchmarks, RFew improves performance by roughly 3 points over R0, which is a substantial margin in this setting. More strikingly, RFew reaches performance comparable to a system called General Reasoner, even though General Reasoner is trained on about 20 times more human-labeled data. Across a suite of math and general reasoning benchmarks, RFew shows consistent improvements, indicating that its benefits are not limited to a single dataset or task type. The paper analyzes why RFew's self-evolution is more stable than prior methods. They track properties of the challenger's synthetic questions over training, such as lexical diversity, length, and estimated difficulty. In R0, diversity tends to collapse and question length inflates, with the model becoming verbose rather than genuinely more challenging. RFew, by contrast, maintains healthy diversity and stable length, while gradually increasing difficulty in a controlled way. This indicates that the challenger is learning to generate genuinely harder but still relevant questions instead of drifting into degenerate behaviors. Overall, these dynamics help prevent concept drift and misevolution. To understand which parts of RFew are essential, the authors run ablation studies on the Qwen 3.8b base model. They systematically remove or modify components such as challenger training, challenger warm-up, and curriculum learning. The results show that grounding the challenger with human examples is critical for good performance. A warm-up phase for the challenger improves stability in the early stages of training. Curriculum learning for the solver yields clear gains on downstream reasoning tasks. Importantly, these components are complementary. Combining them produces the best results, confirming that each plays a distinct role in stabilizing self-evolution. The training process in RFU alternates between updating the challenger and updating the solver. The authors visualize the solver's performance over roughly 100 training steps while this alternation is happening. The curve shows a steady upward trend in accuracy, without the sharp collapses or chaotic oscillations that can appear in unguided self-play. This empirical evidence supports the claim that RFU achieves stable co-evolution, where both the challenger and solver improve together in a controlled fashion. In summary, this paper presents RFU, a guided self-evolution framework that enables large language models to improve autonomously while using very limited human supervision. By combining few-shot grounded question generation, mixed training on human and synthetic data, and an online difficulty-based curriculum, RFU achieves stable and scalable co-evolution. It delivers strong gains on math and general reasoning benchmarks, approaching or even surpassing systems that rely on much larger human-labeled datasets. The work highlights the power of lightweight anchoring to prevent drift and suggests promising directions for extending self-evolution to more open-ended domains, potentially with richer verification methods and improved efficiency.